Hello, everyone. My name is Bryan Feuling. I'm a solutions architect with Harness. Today, we're going to be going over Kubernetes, the super container orchestrator. The intent here is to be very much more on the technical side of what Kubernetes is and how to set it up, but it is going to be a beginner level. So this is ideal for those who have heard of Kubernetes, interested to learn more. Maybe your company is looking to move towards Kubernetes and container orchestration. You just need some a primer on what Kubernetes is before you dive any deeper. This is not going to be business oriented on, why would a business want Kubernetes internally? And this is not going to be intermediate to advanced level information on Kubernetes. So if you've already been through Kubernetes before and you've been using Kubernetes internally, or if you have a CKA or CKAD or something along those lines, this will be a little bit too high level for you. In the agenda, what we're going to do is we're going to cover an overview of Kubernetes. What is it? Why would someone use it? Or why is Kubernetes beneficial? And some of the project statistics, where then we're going to be covering some of the underlying concepts that make up Kubernetes, basically just the architecture. Then we're going to be covering some of the core objects in the API, which is going to be the higher level piece. So what are you actually putting out into Kubernetes or onto Kubernetes and using? We're going to cover some of the security topics as well. And then we're going to hit networking fundamentals. So this is honestly is going to be a high level understanding of just the networking portion of Kubernetes. This section of Kubernetes, the networking piece, can be very difficult to dive into, and there's a lot that can go into it. So we're not going to be covering that in this specific presentation. Then we're going to cover some of the storage and volume. So how do you store state? Where can state live? What about talking to databases? How do we do leveraging like environment variables and secrets and config maps and things along those lines? And then we're just going to wrap it up with a summary. So an overview of Kubernetes. What is Kubernetes? Most who are watching this have heard of Kubernetes before, at least in term. You probably have associated it with Google. So originally Google was building out a couple internal projects for container orchestration and management. They basically combined multiple projects into one main project called Kubernetes. And so this is from Google. It is portable and extensible. It is open source. It is also platform agnostic. Pretty much every cloud provider out there has some form of Kubernetes orchestration that you can put out. And there's a couple other like self-managed capabilities for Kubernetes that are out there where you can just put them on your own VMs if you wanted to. So you could have Kubernetes in the cloud and on-premise and or on-premise if you so chose to leverage Kubernetes in that way. Kubernetes is a Greek word. It stands for pilot or the helmsman of a ship. So you'll notice that a lot of the tools that are used for Kubernetes or that are Kubernetes specific use the same maritime terminology. So, you'll have like dinghies and things along those lines. It's pronounced Kubernetes or Kubernetes. Also, the total number of letters is 10. So the U to the E is 8. You'll typically see people spell out Kubernetes as K8S. And so they'll pronounce it Kates or K8s or K8S. It's kind of up to you on that one. July 2015, first production release of Kubernetes for open source. It was 1.0.1. And right now, the current version is 1.18. There are also 1.19 is in beta right now. So as of this recording, it's 1.18. Why would someone want to use Kubernetes? What's so beneficial about it? So one of the great things about Kubernetes is service discovery and load balancing. So the way that you connect your application to the network and how the network can detect different parts of your application, it's actually relatively automatic. And as a result of that, you don't have to worry about things like setting up a load balancer itself, like a load balancing appliance like an F5. It'll actually connect to services and your network pieces will actually connect to your application code where it's stored, usually the container or the pod. It'll connect to that automatically for you and then scale that. And then it can actually shift the traffic equally among those parts. Then you have storage orchestration. So the idea of the service discovery and load balancing, just kind of move that down into databases and storage and volumes and things along those lines. So this is where another piece that makes Kubernetes very beneficial. Then you also have automated rollouts and rollbacks. So if I go on and do a deployment, it's actually relatively automated. I just say, I declare what I want the state to be, and then Kubernetes will actually direct the cluster to meet that state. And then rollbacks, it keeps a history of how you've been deploying, or what you've been deploying, I should say. And so you can actually get a history, and you can roll back to a previous version if you so chose. You can do an immediate rollback where you just run the command to roll it back. The problem is that it rolls back to the last version, not the last known good version. So just kind of keep that in mind. You also have automatic bin packaging, so you can assign resources to your the objects and resources that you're deploying out. You can assign the resources as needed, and so that you can do like automatic bin packaging and making sure that things are reserved along those lines. Then you have self-healing. There are pieces of Kubernetes, different controllers and managers in Kubernetes that if it sees a bad state, it'll try to correct the bad state. So it'll kill pods, it'll spin up pods, it'll replace pods, it'll scale pods. A lot of that stuff is actually automatically handled by Kubernetes. And then the last thing is your secrets and your configuration management side of things. So if I have a bunch of key value pairs that I want to throw in, whether those are secret key value pairs or plain text key value pairs for scripts or for environment variables or volumes or something along those lines, those are actually decoupled in Kubernetes. Now, you can have them tightly coupled, but the industry standard is to make them as loosely coupled as possible. So those can be decoupled from your artifact, which means you can update your artifact on its own, and you can update the configuration files on their own, and you don't have to worry about those pieces. Some of the project statistics, as we walk through this, you'll want to know, is Kubernetes, is it battle tested? Is it production tested? Is it something that, someone just spun up in their garage, and it's their little pet project, and it's only going to live as long as they feel they have the desire to actually add to it. So Kubernetes is actually very popular. It's right now, 67,000 people have gone to GitHub, to the Kubernetes repository, and have starred it, which is kind of like the GitHub rating system of liking. So 67,000 people have gone to GitHub, and that's not how many people have downloaded Kubernetes and are using Kubernetes. That's just how many people have sought out the desire to basically almost like upvote or like that specific the repository in GitHub. There's 2,700 plus contributors to just the Kubernetes core. There's a lot of ancillary services out there for Kubernetes, but just the core Kubernetes, there's 2,700 contributors to it. You have 50,000 users in the Slack workspace. You have about 91,000 code commits made to date, which is massive, especially considering Kubernetes is a little bit older than 6 years. So 91,000 code commits made to date, that's huge. So now some of the Kubernetes concepts, we're going to be diving on basically the underside of Kubernetes and understanding that portion of it. So here's the architecture, a good architecture diagram for Kubernetes. There's three main pieces. You're going to have the cloud in the top right. That doesn't obviously come with Kubernetes. You don't just spin up Kubernetes and you get a cloud. This is just relating the fact that there are pieces in Kubernetes that correlate to what's happening in the cloud. On the left-hand side, you have the Kubernetes control plane. This is inside of a cluster, usually in a kube-system namespace. You've got a couple pieces that live there. So you have your Kube API server that interacts with literally everything. And we're going to go through all of these different pieces so we just get a high-level understanding of each part. On the right-hand side, bottom right, you have Kubernetes nodes. Each one of these little computer icons, think of it as like a virtual machine or a bare metal server. Those are called nodes. They basically prop up Kubernetes. Kubernetes runs on top of them. And then the nodes have kubelets and kube proxies on each one. So this is just a high-level architecture. So we're going to dive deep into the Kube API server first. And the reason why is the Kube API server is kind of like your REST interface. So everything inside of Kubernetes is done through the Kube API server. Your authentication and security portion is done through the Kube API server. Your interaction with the data store is done through the Kube API server. If you want to run commands against Kubernetes, that's all handled by the Kube API server. So the Kube API server is kind of like the single point of failure in a sense of if you want to interact with Kubernetes. All clients, all other applications, they interact strictly through the API server, and it's the gatekeeper to the cluster. So don't ever delete this, is basically what we're pointing out. Don't ever delete the Kube API server. You're going to need it. etcd, this is one of the main probably the most important piece of your Kubernetes cluster. etcd is the cluster data store. Okay, so what it's doing is trying to provide a highly available key value store for the cluster state. So what exists where and how, what configurations have you set up, what's supposed to be deployed, what's not supposed to be deployed, all of that state about your cluster is all stored in etcd. So when I say it's like one of the single most important pieces, it is highly recommended, and especially if you're using Kubernetes in production, that you back up your etcd as often as possible. If you can make it set up in a high availability where you've got one leader etcd and a couple follower etcds that kind of replicate to each other, that is like the best setup that you can have, because if the rest of the cluster shuts down and you have your etcd backup, it's fine, because your etcd is the thing that keeps the store. So you can literally keeps the state. So you can literally spin up a brand new cluster. You just use etcd, your etcd from one cluster to another cluster, and it'll basically replicate and clone the exact state of the previous cluster. So this is how you can do disaster recovery and high availability with your Kubernetes clusters, is by maintaining that etcd and backing it up. It stores all the objects and configuration information, and it uses a raft consensus to make sure there's a fault-tolerant, consistent view of that cluster. Then you have the kube scheduler. This one, this part of your architecture, you'll get a few errors from that are going to be kind of interesting. So the intent of the kube scheduler is it basically makes sure that everything is scheduled to exist on certain nodes and certain parts of your Kubernetes cluster, your architecture. So when you say, I want a certain amount of pods, or I want a certain amount of services, or I want a certain amount of deployments or replica sets, or whatever you want to call it, your kube scheduler is the thing that makes sure that those things get scheduled, those objects get scheduled inside of your Kubernetes cluster. So it looks at, there's a huge amount of things that the scheduler makes a decision based off. So what are the resource requirements of the object you're trying to deploy? What are some of the constraints for the hardware, the software? Do you have a policy constraint in place? Do you have any affinity for a node? Do you have data issues that you need to connect with? Do you have inter-workload interference? Do you have any deadlines? The kube scheduler keeps tabs on all of these different factors and interacts with the kube API server to understand that, and then will schedule your objects or your resources that you're deploying into Kubernetes. It'll schedule those out appropriately. Now you have the kube controller manager. So we've talked about the kube API server, which is the main REST interface. All of the other components talk to the kube API server. You have your etcd, which is your state or your cluster state backup piece, like kind of like your database. You've got your scheduler, which schedules everything that it's supposed to go out. But when you understand where things are supposed to be scheduled, and you understand what you have available and what your desired state is, there has to be a component inside of Kubernetes that actually steers your entire cluster towards that desired state and away from an undesired state. That's actually what the kube controller manager does. So it actually has multiple controllers that it manages, and then those different controllers will actually monitor the cluster state, and then the kube controller manager steers the entire cluster. So one of the controllers is a node controller. It controls the nodes and makes sure that the nodes are up in the desired state. And if they're not, you get warned, you get notified, maybe spin up a new node, things along those lines. You also have replication controllers. So if you're saying, I want to deploy this thing out, but I want this like a pod, I want to deploy this pod out. I've got a pod that's out there. I need 3 of those pods. The replication controller make sure you scale up to the 3 pods, because you declared that you wanted 3. So you declare your desired state, and your replication controller is going to maintain that desired state. It'll also do this in regards to scalability. You also have endpoints controllers. So this is how Kubernetes will, or the kube controller manager in Kubernetes will make sure that your pods and your services are actually connected. So essentially, how do you get network traffic to your application code? The endpoint controller is the thing that's going to steer that to the correct state. And then you have service account and token controller. So you have default accounts that need to be created. You have API access tokens that need to be created for new namespaces. And so the Kube Controller Manager will actually maintain that portion for you. A relatively recent addition to Kubernetes is your Cloud Controller Manager. So it's essentially the same as the Kube Controller Manager, except it has to do with all of the underlying infrastructure for your cloud. So is your cloud nodes, your EC2 instances, your GCE instances, your VMs, are they being spun up and maintained at the state that they need to be for Kubernetes to work? How about routes? So you have underlying network requirements inside the cloud to make sure that everything can talk to each other, like ELBs and ALBs. Okay, well, that's what the route controller is going to do for you in the Cloud Controller Manager portion. Then you have service controller, so making sure that the load balancers inside of the cloud are actually set up correctly. You've also got volume controller, so your data storage inside of your cloud is actually spun up and is at a desired state for Kubernetes to interact with. Now we're going to jump into those nodes. As we mentioned before in the architecture, you have your Kubernetes controller section of control system, and that has the Kube API server, the etcd, all of those pieces. Then you have the different machines that are kind of propping up Kubernetes. Those are called nodes. They're basically just, think of them as VMs or bare metal servers. Well, in order for those to interact with Kubernetes, the control plane in Kubernetes, and for the control plane to talk down to those nodes, so that way you don't have, just random VMs spun up everywhere and not really understanding if they're up or down, or how do you interact with them, or what's the network going to look like, how do you schedule containers and pods to go out onto those nodes. So what we have is agents that live on each individual node. So one of those is a kubelet. It makes sure that the containers are running in a pod. So if you have pods that are being deployed to the node specifically, the kubelet makes sure that the containers are running. It takes those pod specs that are assigned to that node from the kube scheduler, and it makes sure that it's running and it's healthy, what it's supposed to do there. There's one more agent that handles basically the networking side, which is the kube proxy. So a kubelet and a kube proxy exist on every single node and make sure that all of the network is actually handled appropriately. The last thing is the container runtime engine. So it's a container runtime interface compatible application. It executes and manages your containers. So the most popular one obviously is Docker. So if you've heard of Docker, you probably have heard of Docker because you're looking at Kubernetes. Docker is the obviously the most popular of all the container runtime engines that are out there. Then you have a couple other like Cryo, Rocket, Kata, Vertlet. So there's a few that are out there. Obviously, Docker is the most popular one that's there. So now we're going to talk about some of the core objects in the API. This is more on the high level side of Kubernetes in the sense of what are you actually going to be interfacing with on a regular basis. So the previous section was more, it's good for troubleshooting, but your certified Kubernetes administrators or your Kubernetes administrators themselves are going to be maintaining that portion and setting those pieces up on the back end of Kubernetes. This portion of the presentation is going to be talking specifically towards what will you be interfacing with most likely on a regular basis. So the first thing to know about Kubernetes from the practical side of interacting with it is, what is Kubernetes YAML? That's going to be one of the main ones, because you're going to be seeing errors and issues when you deploy if you try to build your YAML from the ground up. So how do you dissect it and understand quickly what you're seeing? So this is what Kubernetes YAML looks like. The four main sections of the majority of the Kubernetes YAML manifests is what they're called. So this whole section on the left is a manifest. So the majority of them are going to have four main sections: the API version, the kind, the metadata, and the spec. And inside of those four versions, you have nested sections that need to exist. So the API version basically tells you which version of Kubernetes API are you wanting to use. That version automatically associates to a kind. So for example, you can't have a pod exist in a V1 beta 1. Pod always exists in V1 API version. So think of an API version as like a bucket, and then inside that bucket, you have a whole bunch of kinds that you can actually use. So that's what the kind is, or the type of object. You have metadata. This is about uniquely identifying this object that we're deploying out. So when we deploy this pod, we can do searches inside of Kubernetes and say, okay, well, what's the name? I want to find all of the MyApp pods. Okay, so I'm going to go search for pods that are called MyApp pod. And then you also have labels. So if I need to associate this pod with another set of objects and services that are out there, I might give all of them labels app, my app. So now I can uniquely identify this pod, and I can also uniquely identify all of the different objects associated to app, my app. Then you have a section at the bottom called spec or specification. It's basically what's the desired state of this pod. So the desired state is to have a running container inside of it. We want to call the container PHP Redis. The image or the Docker image that we're going to be using is from the library. It's called front end, and the version of that container we're going to be deploying out is v3 in this case. And then we have a container port, port 80, which is how we're going to talk in. So you have namespaces. This is you probably won't be creating this, but you'll be interacting with namespaces on a regular basis. This is basically how do you partition a cluster so you have logical sections of your cluster to interact with. So you can do, maybe you have multiple customers and you want all those customers to exist in the same cluster. You can spin up a namespace per customer. So namespace customer A, namespace customer B, if you wanted to do that. You can also do environments based off of the namespace or internal teams based off of the namespace. It's pretty basic, but it's about partitioning that cluster. Again, typically speaking, you're not going to be creating your own namespaces. That's something that a Kubernetes administrator will be doing. But if you ever wanted to go and get information from a namespace, like what pods exist, what services exist, configuration maps, things like that, that is all going to be done most likely via the namespace. So you'll see on the right-hand side, we have kube control get namespace. That's the command to find out all the namespaces that exist in the cluster. Right now, we've got 4 default kube system, kube public, and app. App is the one that we're creating from the left-hand side, as you can see. Now we're going to move on to pods. This is an interesting one. It's good to know what a pod is because it's the basic execution unit. It's the smallest set of unit of work in Kubernetes is the pod, the smallest one that you've got. This is the pod on the left-hand side, the pod YAML. We've already talked about what the pod YAML is. And this is how you search for a pod. So kube control get pods. Again, I mentioned before on the last slide that you're not going to be creating namespaces, but you might be leveraging namespaces to search through. So if you did kube control get pods and then you declared which namespace, it'll get all of the pods in that namespace. So if you know you deployed a pod, and you go and run this kube control get pods and it's not showing up, check the namespace to make sure that you're actually searching in the correct namespace. Now, what's interesting about pods is you typically speaking will not be deploying individual pods like this. You'll usually be leveraging those controllers, the replication controllers that I mentioned before, which will be like a deployment or a stateful set or a daemon set. So you'll use a higher level of abstraction. And the reason why is a pod is, if you deploy it this way, is actually a what's known as an immutable object. It can't be changed. So if you deployed this out and you gave it the wrong app, and it's supposed to be my dash app and not my app for the app name, well, you can't just go and update this pod. You actually have to delete it and then redeploy it out because it's immutable. If you have a replication controller instead, the controller will handle all of that for you. You can update the controller information. So you can update the deployment object, you can update the replica set object or something along those lines. And then that specific object will be leveraged by the replication controller to tear down and spin back up a new pod automatically. So that, again, you won't really be deploying out individual pods. You'll be deploying out a higher level abstraction or what we call a workload instead. Now you've got a service. So if a pod was the smallest unit of work, a service is essentially the smallest unit of network interfacing. That's the point of a service, is to interface your network traffic with your actual pods. If your pods just live there and there's no service tied to it, there's very few ways you can interact with the pod and the containers on the pod. And you have to know a lot of information about the pod in order to interact with it without a service there. So this is what a service looks like on the left-hand side. It's basically saying we're looking at port 80 and the target port is 9376. So that's the bottom section there. And we're saying we're going to attach this service to any app or any label app, my app. So if you have a whole bunch of pods that exist out there or other objects that are available, like your deployments and things along those lines, if you put in the label app, my app, this service will automatically discover those services and then can balance that traffic load for you automatically as a result. And this is how you run it. Kube control get service, same as kube control get pod. So, and then you'll see the output there. So you have a couple different service types. You have something called a cluster IP. This is the default service type. So if you don't declare which service or which type you want for service type, it'll just automatically put in the cluster IP. The cluster IP is an internal IP address. That's basically what it is. So your service, we mentioned on the last slide that if you put in selector app my app, let's assume that's what we did. The pods on the right, they have the label app my app. Therefore, the service is automatically tied to them. The service on the other side actually has what's called a cluster IP, and that's basically how anything inside of the cluster can interact with that service, and then as a result can interact with the pods on the underside of it as well. Again, this is the default type, is the cluster IP. Then you have what's called node port. So this is the ability to expose the node IP and port to a service and to external traffic if you wanted to do that. So you can do this by saying what's the node IP address and what is the node port that you're trying to talk via, and that's kind of how you interact with it. So what you'll see here is you have a service on the left. You've got your nodes, and remember, nodes are the VMs or the actual servers. You've got pods on the nodes. And so if you wanted to interact that way, you could say, okay, the service is going to interact with this designated node port. Or if I wanted to go talk to that pod, I would say, okay, what's the node IP and then what's the port that I want to talk over? So that's actually what's going to be happening there. Then you have load balancer. This is the most common type of service if you wanted to interact with external traffic. There's a couple other ways to do that, but load balancer is one of the most common ways to set this up. So the load balancer will actually create a cluster IP on the service that interacts with external traffic. And then we'll also create a node port to talk to as well. So it'll actually forward all of that traffic automatically for you. So you just spin up the load balancer as the service type. So when you spin up that service YAML and you if you build out the YAML for the service, there is a section in the spec where you can say what type of service do you want it to be, and that's where you can put cluster IP, although it's default so you don't have to, but you can also put node port. You can also put load balancer if you wanted to do that. Then you have ingresses, which is traffic ingress. And so this is a way to expose all of the HTTP and HTTPS traffic from external sources into your cluster through a service if you'd like to do that. So you've got your ingress, you can take external traffic into your ingress, and then your ingress will define like path-based routing if you'd like to do that via HTTP, HTTPS routes, and it'll direct it towards different services, and then those services will direct that towards the backend for the pods if you wanted to do that. Then you've got, again, this is about as low as we're going to get into the network portion of things. We can get very deep. This is a huge area of Kubernetes, is understanding ingress and understanding service mesh and understanding traffic and load balancing and traffic weighting and all of that. But we're not going to be doing that right now. So what we're going to do is we're going to talk about workloads. We mentioned this before, that you're not going to be deploying out individual pods. You'll typically speaking be deploying out workloads. So you'll have what are called replica sets. It's basically just to make sure that the state of the amount of pods that you want is always going to live. So if a pod starts to die and you say, I want 2 or I want 1, the replica set will make sure that if it dies, it dies and you spin up a new one automatically. So it'll see that there is a state that is different than what you desired and declared using the replica set, and then it'll actually spin it up. So this is what a replica set looks like, and this is what the YAML looks like. Now, again, this is an interesting one because you typically speaking won't be spinning up replica sets, right? So instead, you'll be spinning up what are called deployments. And it wouldn't surprise me if deployments just completely get rid of replica sets at some point, but you'll mainly be interacting with deployments. It provides declarative updates for your pods and your replica sets. So this is what it looks like. You've got a deployment that spins up a replica set. You have a replica set that spins up multiple pods. So if you were to go to Kubernetes after running a deployment, if you deleted one of those pods, the replica set would want to spin up that pod. If you want to delete the replica set, the deployment would make sure that a replica set exists in the desired state. If you want to delete all of that and actually not have it exist in your cluster anymore, you need to delete the deployment. As a result of deleting the deployment, everything downstream will be deleted for you. That's related to this. And this is what the YAML for a deployment looks like. So this is the important things. We're going to park on this deployment YAML for a second. So you're declaring which version of the API, as we said before. So you'll notice this apps v1, that's where the kind deployment lives. So if you were trying to do v1 and you wanted to declare a deployment kind, it won't work. So sometimes you'll get an error that actually tells you there is no deployment in API version v1. Well, go back to your YAML and make sure that your API version is correct associated to the kind that's needed. In this case, we have metadata, which we're declaring this deployment. It's going to be called front end, and it's got two labels. It's got guestbook, app guestbook, and tier front end. Then that deployment, you're basically making a desired state specification in the spec section. So you're saying, I want to spin up 2 replicas of something from the template section and below. And then what I'm going to do is I'm going to match these labels of this tier front end. So I'm actually going to make sure that the anything that's deployed out, I want to make sure that they have tier front end tied to it, so that all my services, my network services, can all talk and be automatically discovering these services as they scale up and scale down. That's the point. Then you have a template section inside the spec where you're basically saying, I'm going to create a template in this deployment, and I want to have X amount of replicas associated to the template section. So right now I've got 2 replicas in my replica section up right below the spec. And then my template is going to say, this is what I'm going to build out. So it's going to be a pod. So deployments build out as pods. I'm going to have a pod, and it's going to have certain metadata. So it's going to have a label, and inside the label is going to be tiers front end. And then each pod is going to have a desired state, which is going to be a container inside called PHP Redis. There's the image and the version, and then there's the port number. So now if I run and deploy this out, what's going to happen is the deployment will create a replica set. The replica set will take all the information below spec, and it'll actually create 2 replicas for me, so 2 pods of the information inside of the template section of the deployment. Now there's 2 other types of workloads that we're going to be interacting with as well. So one of those is called a daemon set. So when we're dealing with application performance monitoring or log aggregation, or we want to make sure that there is some type of monitoring something on every single node or VM inside of Kubernetes, we would use something called a daemon set. So it makes sure that there's at least 1 copy of a pod running on every node or every designated node type. So you can actually say, maybe not all nodes, maybe only the reserved instances I want something to live on. So this is what it looks like. Your daemon set will deploy out onto a node, a specific pod. That's what it does. And this is what a daemon set, so you see it's a fluent logging for Elasticsearch here. So you can see that we're using volumes, and we've got this designated container and how much is the resources it's going to be taking, and what is the toleration set here. So it's going to be looking for all of the nodes, and the effect is no schedule. So I want to make sure that, the pod exists on the node or on a certain set of nodes, and that's what a daemon set's going to do. We have another workload, though, called a stateful set. This is not necessarily related to daemon set itself. This is actually a little bit closer to the deployment side of things. So a stateful set is, I should say, typically speaking, at least an industry standard, we want as much in stateless as possible. There are some good use cases for stateful sets, but we want as much stateless as possible. And the reason why is state is the current understanding or what is known as state. So current state or current understanding of the designated pod and containers inside of the pod. So you'll be storing information about the pod, storing information about the container inside of the pod. The problem with a stateful set is if your pod dies, you lose all of that state. So be very careful on how much information is stored inside of the pod, inside that stateful set. Again, there's a couple good use cases. So one of the benefits of a stateful set is there are certain identifying factors on the stateful set that will remain, and you can update the container internally. So that you might have some type of like agent-based application system or appliance or something along those lines where you want to update the container or the application code inside, but you want to keep the pod around, right? You don't want it to die and then spin up and die and spin up. So this is really good if you want to make sure that there's always a designated amount of resources. So here's a really interesting hypothetical scenario. Let's say that we need something to exist on a node or inside of a cluster, and the cluster doesn't have a lot of resources available. Well, if you're actively deploying different pieces out into the cluster, but you need to make sure that a certain amount of resources are reserved for one specific appliance in the cluster, if you just delete the entire appliance, you cannot be guaranteed that the next time that you execute it, which hopefully is immediately, that it'll actually have enough resources to spin up. So what you can do is set a stateful set which will actually create and reserve a certain amount of information for a pod. And then instead of updating the pod each time, you can actually update the container inside the pod. So you have a designated amount of resources always available inside for that pod. So that's one of the use cases for a stateful set. So there's a stateful set. So it basically creates a pod, and then the pod has a state inside of it. And this is what it looks like to spin up a stateful set. Again, API version apps v1, kind stateful set. And you're basically saying, I want 3 of those replicas, or 3 of those pods. And then I've got a grace period for termination. Here's what the containers I want to exist are. Here's the volume mount. So internally inside the pod, here's the volume mount that I want it to be able to leverage. And how big is that storage? Another workload that you might come across every now and then is called a job. So imagine if I wanted to run a testing suite. I want it to run once. I want it to, when it's finished, I want it just to automatically delete and maybe send the logs or the output of that test somewhere when it's finished. But I don't want it to persist. I don't want it to consistently stay. I just want it to run once and it's done, also known as ephemeral. And that's actually what a job is. So most common use case I've seen for a job is literally to run a test. So you build out your test, you put it inside of a container image, and then you run a job which just spins up the container, runs the test, tears it down, and you're done. So a job basically just creates a pod. Now, if you delete the job, it'll delete the pod that's associated to it automatically. You can also put things inside of the job spec that are pieces inside the job spec that declare that you want it to be deleted when it's finished. But this is an example. I want to run a job which is going to spin up a Perl container image called pi, and it's going to run the Perl command that's here, and it's going to print out pi, and then it's never going to restart type scenario. And this is essentially what a job is. And then maybe I'll go in and delete it later. Now, at the same time, I might have a job that I want to run, but I need to run it every 45 minutes or an hour. Again, for the testing piece, I have an end-to-end test, and I want to run that end-to-end test every hour in the cluster to make sure that, maybe there's some loosely coupled services inside of the cluster, and I want to make sure that the versions make sense together and that they're talking to each other and there's no other issues. Maybe I've got intermittent user traffic because it's overnight or something like that, right? So I actually want this job to consistently run. Well, instead of setting it up where I have to go and run this job every single time, I'll use a different workload called a cron job. And it basically creates a cron job basically creates a job at a designated schedule. So a cron job creates a job, the job runs the pod. So you've got the cron job, and it's basically you're saying run this job on this designated schedule, and here's the template of the job. So very similar to the deployment where you're creating a template of the pods that you want to exist out and how many replicas you want of those, of everything inside the template section. It's the same thing with a cron job. You can run it on a schedule, and you can say, here's my job template, and here's the job that I want it to run. So now we're going to cover some of the security portion of Kubernetes. Again, this is going to be something that your Kubernetes administrator will mainly maintain. You'll probably interact with your Kubernetes cluster using some type of MFA or 2FA or through some third-party application. You, typically speaking, won't be going straight into the cluster itself unless you're spinning up the cluster or you're the Kubernetes administrator. But it's important to know how the security works, so that way, if you find that you have certain errors or issues with the ability of a solution that you're using is not able to execute certain commands or interact with a certain namespace or a resource, there's probably a role-based access control issue inside of the cluster. So here's the access control diagram. It's basically how does Kubernetes allow you to run your authorization, authentication, and then your admission control into Kubernetes to execute whatever the commands are that you want to execute. So the two main actors is going to be either a user, so an external user, an external service, an external, bot, something along those lines, or a pod. So you have a pod internally that wants to be able to interact with Kubernetes. So the first thing it's going to do is it's going to interact with the Kube API server. The Kube API server is going to run through an authentication process. It's going to say, how are you trying to authenticate into Kubernetes? Are you using a certificate? Are you using a token? Are you using a username and password? What are you doing? Once you pass that barrier of authentication, then the Kubernetes API server is going to say, okay, based off of how you've authenticated, this identifies you as, user A or user B. Now I want to authorize you and see, or I should say, see what you're authorized to do. And is the command that you're doing something or executing, is that a command that you are authorized to execute? If it's not, I'm going to spit back an error and say, you don't have that permission set. If you pass the authorization, then I'm going to go to the admission controller inside of the Kubernetes API server, and the admission controller is going to say, okay, you've authenticated in, you're authorized to execute the command that you want to execute, but I've got some higher level policies that are set. And the Kubernetes administrator has set these certain policies to limit the amount of executions of your designated command against Kubernetes in the cluster. So I want to make sure that maybe there's a higher level limit so we don't overload the system in some way, shape, or form. So you can't just consistently ping the cluster for pods. If you pass all three of those barriers, you'll actually be able to execute the command that you wanted to execute. The way this is done, first in authentication, you can do it through an X509 client cert. You can do it through certain static files, a password file or a token file. It's not the most secure, but at least it's more secure than just leaving it wide open. You can do bearer tokens. So it looks like this authorization : bearer, and then your bearer tokens. You can do that. You can also do bootstrap tokens, which it's kind of like a bearer token, but it's a different type of token output. You can do a service account token. So you can actually set up a service account and then give that service account a token for it to do certain things. This is very common with, vendored solutions or different solutions and tools you want to interact with Kubernetes that need certain permissions. You might create a service account, assign that specific solution or tool the service account, and then the token it can use. A more recent one is using OpenID Connect token. So it's a JWT or a JSON Web Token. And it uses basically the token from an OAuth 2 token response. So you can also leverage that for authentication. So for your authorization, this one's interesting. You can use what's called a role or a cluster role. So a role is a set of permissions, but you assign it to a particular namespace. A cluster role is a set of permissions, but that is not designated to a desired namespace. So a role might be, go get all the pods inside of namespace default. A cluster role might say, go get all the pods, period. And you can execute this on any of the namespaces you want to. And you can't have both in one role. You can't create a role that is a role and is a cluster role. You have to have one or the other. So this is what a role and a cluster role YAML looks like on the right-hand side. Notice the API version is part of the RBAC.authorization. The kind is role or cluster role. So those are the two kinds that you can have in that API version. The metadata, you'll notice in the role, the metadata is declaring the namespace as default and then giving a name to that role. And then what you're going to do after the role is you're going to give it the rules. So anybody who has, or anything that has the pod reader role assigned to them now has the following abilities. They can get, watch, and list all of the pods inside the namespace default. That's what they can do. In the bottom section for the cluster role, we're going to create this. Again, it's not a namespace, so you can't assign a namespace to a cluster role. We're going to give it the name secret reader. So any user or system or service account that has secret reader assigned to it, what it's able to do is basically do a get, watch, and list on the secrets inside of the cluster. So it's not namespace specific. Now, once you've created these different roles and cluster roles, you'll notice we're not assigning them to anything yet. This is done through something called a role binding. So in role binding, you can say, I want to assign a designated role to a designated user or system or group. So in the top here, we're saying, okay, the user Jane is going to be assigned the role pod reader. So that's how we take the role that we created in the last slide, and we're going to take that role and we're going to assign it to the user Jane. Same with the cluster role binding on the bottom, except for this time we're going to say there's a group of people called managers, and that group of managers can now be assigned the cluster role secret reader. So if your user is associated inside of the group called manager, you now will get the secret reader capability. And that's essentially what a cluster role binding is. Then you have the admission controller. This one's pretty interesting. We're going to go through it again in the summary section, but the admission controller, relatively new. It's still being built out, but it's the idea of limiting all of the requests to the Kubernetes objects. I'm not going to read through all of these. There's a lot of admission controllers that are available for you, and they're consistently being added to on a regular basis. So now we're going to go through the fundamentals on the networking side. This is going to be really short. Again, we're not going deep into the networking piece, but just so you understand how to interact with the different objects inside of your cluster. So fundamental networking rules. If you have multiple containers in a pod, they all can talk to each other without any issue. You know, it's kind of like having a whole bunch of computers that have a LAN cord directly connected to every single one. Pretty simple to talk to. You don't need any special networking appliance like a load balancer or anything to talk to them. It's the same thing. Now, all of the pods inside of a cluster, they can actually communicate with all the other pods without a special network appliance inside of the cluster. So you just need to know what the pod IP addresses are, and you can just communicate with those. All of the nodes inside of a cluster can communicate with all of the pods inside the cluster with, all the nodes can communicate with all the pods that are in the node. So a node, individual VM, it's got its own IP address. And when you spin up a cluster or spin up a pod, you can actually have the node interact with all of the pods and containers on that node. So it can all be done. The IP address that the pod sees itself as. So if you have if you look at all the network addresses inside of your node, you'll see the pods have their own IP addresses. A lot of times they're going to have the same IP address as another pod in another node, because the whole private IP stuff. Again, we're not going to go super deep, but it's going to see itself as the same IP that everybody else is going to see it as. So you're not going to be looking at a pod and it's not going to have the loopback IP address on it. Right, so that's not going to exist. So all of your pods need to interact with a service, and this is managed by the kube proxy. And then it actually will exist. This relationship can exist beyond the pod. So the service is independent of the pod. If you have a service tied to a pod and the pod, you know, spins down or dies or anything like that, it doesn't mean the service does it as well. The service is decoupled. But the service has pieces inside of it that declare, you know, basically directions inside that say, okay, all of these pods that are of type A or have label B or whatever, the service will automatically discover those and attach itself to those pods. But if the pods die down, the service doesn't care. It's just going to still live. So it exists beyond that pod's life cycle. The other side of the service is external sources talking to the service. So you have a pod that talks to the service and service talks to the pod on one side. On the other side, you have external items talking to the service and the service able to talk to external items as well. This is also handled by the kube proxy, and it works in cooperation with the cloud provider or some other load balancer that's out there. So again, this is super, super high level, and how do different objects and entities inside and outside of the cluster talk to each other. It's important to understand how that relationship takes place. So now we're going to talk about storage and volumes. This is going to be a rather long section, and it's because there's so many different storage and volume types and classes that are out there. So we want to make sure we cover them appropriately. So what is a volume? It's basically just a directory or a file hierarchy with some data in it. That's essentially what a volume is. You put a volume inside of a pod and the containers can talk to that pod, very similar to a stateful set. So this is what it looks like: pod, container, volume. Pretty basic stuff. And this is what it looks like inside of the pod YAML. You are basically saying which volumes are you going to use. So the volumes is the bottom section. This is the name of the volume. This is what we're going to leverage. And then you're mounting the volume to the container. So pod has a volume, very bottom, and the volume is mounted to the container. So the container knows to use that volume. That's basically what it is. There are a ton of volume types. So again, your Kubernetes administrator will be the one that maintains this process or helps with this process as needed. Then you have something called a persistent volume. So as you saw in the last diagram, you have a pod, and inside the pod you have a container and you have a volume. But if the pod dies, the volume dies with it. What if we wanted the volume to exist outside of the pod and we want multiple pods to be able to interact with that volume? That's essentially what a persistent volume is. So you have a Kubernetes cluster, you have persistent volumes in the Kubernetes cluster as a whole, and then you have pods interacting with that persistent volume. And this is what it looks like on the right-hand side. So what is the access mode? Read write once. You're going to recycle the reclaim policy. So if all of the persistent volume claims, which we're going to talk about in a second, are talking to that persistent volume, if they all die off, what do we want to do with the persistent volume? So a persistent volume claim is how you associate a pod to claim part of that persistent volume that exists external to the pod. So how does a pod interact with a persistent volume? It does it through a persistent volume claim. And this is essentially what it looks like. So you've got your YAML on the right-hand side. This is basically the persistent volume claim that a pod will be using. There's the volume mode, the storage, and then what it's going to be matching itself to. So release is stable, match key expressions, things along those lines is just how it interacts with it. Then you have a storage class. So this is, again, at the Kubernetes administrator level. It describes the classes of the storage that Kubernetes will offer. And so you can have different storage classes that are available to you. So you've got the provisioner or the driver for provisioning the storage. You have certain parameters for configuration, and you have your reclaim policy. So when your persistent volume claim is deleted, do you retain it? So in this case, we are retaining it, which means you have to manually go to that storage and clean it up. So you might want the data to live regardless of the lifecycle of the pod and the persistent volume claims that the pods are using. If you put it to delete, then the storage class itself will actually just auto delete if all of those persistent volume claims are deleted. And then again, you have a bunch of storage class types that are out there. So now we move on to an interesting one called config maps. You've probably heard of or seen config maps before, but the idea of a config map is if you think about traditional applications, there's usually something called environment variables where you want your application to be able to use information from the environment that the application lives on inside of the application code. So, maybe a database connection rule or a network rule or network route or something along those lines. So your server, your VM will be spun up with those environment variables inside of them. Your application will be deployed or copied to the virtual machine itself. And then as a result, it's looking for the key value pairs that give it, what is the database connection? What is the network route I'm going to be using? A config map is kind of like that, but it exists external to the pod. So that's, and this is plain text key value pairs. So you might want to say, maybe you're using an APM agent of some kind and you want your all your APM agents to use the same environment variable and value per environment that's out there. Well, I don't want to create multiple versions of the manifest for that agent. I want to be able to just deploy it one version of that manifest. I just want to deploy that out into the cluster. And if it's the dev cluster, it's going to look for certain environment variables to use and modify its behavior as a result. Same with QA cluster, test cluster, UAT cluster, production cluster, things along those lines. That's what a config map essentially is. So similar to a volume, because it is a volume, a config map lives external to the pods. And so this is what a config map essentially looks like. So V1 config map, what's the name of the config map? Game demo. And what are some of the environments it's going to be using? Player initial lives, 3. If you were maybe deploying your game demo out into a dev environment, you might want to give it, player initial lives is 100 because you want your player to die a lot and live and die and live and die and not be hindered by the 3 lives rule. But in production, you might want to set it to 3. So we can have a config map in dev where player initial lives is set to 100, and we're going to have a config map in prod where player initial lives is set to 3. So now I don't have to change my code in my container to have one that's set to 100 and one set to 3. I just say, go use whatever the value is from the player initial lives in this config map. That's essentially what this is doing. A secret is basically just a config map, but you have secret values and key values inside of it. That's essentially what a secret is. So database connection strings, probably something we want to keep secret. OAuth tokens, again, something we want to keep secret. So this is what it looks like for the secret. You have a couple different types of secrets that are out there. So you have a Docker registry secret. So this can be used to interact with your Docker registry and be used to pull down your image. You have generic or opaque, which is literal values, which is what we're using in this case. And then you have TLS. So if you have cert-based secrets, that can be the type as well. And then you have your data in the bottom. You can set multiple data points, username, password, whatever you want to key value pair call it. And so you can see these are base64 encoded as well. Then you have the question of if your configuration or your config map or your secret or your volume, if those things exist externally to the pod, how do we get the key values to work with our actual application code? So you can leverage this using what's called environment variable injection, where you're basically saying, here's my environment variable for my game demo. It's called player initial lives, and I have another one called UI properties file name. In my config map, I'm going to be using player initial lives, and I'm going to be using UI properties file name. That's the keys, and I've got the values associated to it in the config map. So what I'm going to say on the right, you can see here, spin up this pod. It's going to be this image. It's going to have two environment variables that it's looking for, player initial lives and UI properties file name. That's what the container's wanting to use. As a result, we're going to mount the game demo config map. And then in the game demo config map, we're going to be using the designated key. And that's basically what we're going to be leveraging. And this is how you inject per environment variable. You can also do something similar, but with a command. So let's say I wanted to leverage certain information from a secret, and I wanted to pass that into, a pod or a job or something along those lines. So here's the idea of the pod. It's got a command echo special level key, special type key. So it's going to be using that from a config map, special config, and there's the key that it's going to be leveraging. So this is a way of injecting the key value pairs from your config map or your secrets into a command. Then you also can do this from a volume-based injection. So you can actually mount your config map or your secret as a volume for your pod. So you'll see that on the right-hand side. So we've got the containers at the top. We have the volumes at the bottom. The volumes, the name is called config volume, and the config map name is special-config. And so now my container, it already knows to use whatever the volume key value pairs are. So we're just going to mount the volume in, and then that's how it's going to be leveraged. So as you can see, we declared a mount path. So we're saying, here's the volume. Okay, so in the container, we're saying mount this volume on this specific mount path. So now I'm going to go look in that mount path for all the key value pairs in etc config. So that's how you can inject it as a volume. All right, so we're going to go over a basic summary. So Kubernetes Overview, it's developed by Google. It's portable, extensible, open source. It's 6 years old, older than 6 years now. It's 2,700 contributors to the Kubernetes core. So it's a ton of different developers are contributing to Kubernetes to make it beneficial and production hardened and reliable. It's pronounced Kubernetes, or you can see it with a K with the number 8 and then an S. So Kates, K8S, K8s, depending on how you want to pronounce it. Current version is 1.18. Some of the concepts to understand. So Kubernetes architecture, it's made up of the Kube API server, which is that REST front end to interact with the Kubernetes cluster. You have etcd, which is the cluster data store. You have the kube scheduler, which does all the scheduling decision-making for your containers. The kube controller manager, it steers the cluster to the desired state. The cloud controller steers the cloud to the desired state for Kubernetes. Your kubelet is one of the agents on the node for container management. Your kube proxy, it's the network agent on the node for network management. And then your container runtime engine, such as Docker, Cryo, etc. Your core objects and API, Kubernetes YAML requires, in pretty much every circumstance, requires an API version, a kind, a metadata, and a spec. There are a couple nuances to that, such as config maps, as we saw, role-based access control pieces as well. The Kubernetes.io website is a great site to go to if you want to understand what should go in which YAML, but the vast majority of the objects you're going to be interacting with is going to be requiring API version, kind, metadata, and spec. Namespaces, the primary way to partition a cluster. A pod, the basic execution unit of Kubernetes. The service, the basic network service of Kubernetes. Workloads are different controllers that declare the desired state and spec of all of the pods that exist out there. So you've got deployments and replica sets, you've got jobs and cron jobs, and you've got stateful sets and daemon sets. So different workload types that are basically controllers that have they steer the cluster towards a desired state. Your Kubernetes security, so your access control, all handled by the Kube API server. Your authentication is done by a pod or a user through a cert, a token, or a security file. Your authorization is enforced through role, cluster role, and then binding your users or your groups or your service accounts to those roles or cluster roles. Your admission controller, it essentially just governs and enforces how the cluster is to be used. That's a really high level understanding of an admission controller. Kubernetes networking, all the containers in a pod, they just can talk to each other whenever they want to. Nodes and pods in a cluster can communicate without a special application or appliance inside of them. Services enable communication from external pieces to your pods and vice versa. Storage and volumes. So volumes, they act as storage for containers. That's basically what they do. Persistent volumes, they are independent of the pod lifecycle. You can have different classes of storage defined by your administrator, called a storage class. Pretty simple. Config maps and secrets. This is how you decouple key value pairs from your actual containers and pods. And that's essentially everything. Thank you so much for joining us on this Kubernetes presentation. If you have any questions, reach out to me. It's Bryan, Bryan, @harness.io.